close mean in statistics? Here's the problem that a lot of you guys, I think, still have. I can see it every now and again on problems. Is 1 close to 1.1?
It depends.
It depends. Exactly. If my standard deviation is 0.000001, is 1 close to 1.1? Hell no. It's a lot of freaking steps away, right? So the word close is not good enough. Are you guys with me? I've got to bring the standard deviation in there somewhere. That's how I define distance in statistics, right? So I can't just say to somebody, I think it's about this, give or take something. It's kind of close to that. I have to give them an idea of what close is in this case, right? That's where this formula comes in. So here's the missing ingredient. I want to make an interval like this. There you go, Jeff. You just did it. What's your problem? Done. I want to figure out what these numbers are. So I can tell somebody that I am 95% confident that the real income for San Diego, the real average income, is between this and this. I want to know what those numbers are. This should sound vaguely familiar. I've made you guys do this so often. Go from the mean and go up and down so many steps, right? You guys have done that kind of thing many, many, many times. It's the same stupid thing. It's the same thing. The only difference is now, if I want to be 95% sure, 95% confident that I catch the right data point, that I catch the mean, that this interval will catch the real mean, what percentage of the data should I catch to be that sure? So if I want to be 80% confident that I caught the right kind of fish, what percent of the fish should I catch? 80% of them. Then am I not 80% confident that I caught the right fish? Because what's the chances I didn't? 20%, the 20% that I didn't catch. So how much of the data do I want to catch? It's almost too simple. If I catch 95% of the data, I am 95% confident that that will catch the real mean. So what is 95% confidence? Exactly how many steps up and down is that? It's not quite 2. It's close. I know empirical rule said 95% within 2, but we know that that's kind of an approximation. It's actually 1.96. And how do I get that? 95% sure, right? How much is in here then? 0.025. If you look up 0.025 in the chart, you'll get negative 1.96. 0.025. Yeah, so right there, it's exactly 0.025, negative 1.96. So it's 1.96 down and 1.96 up. So if I start the mean and I go up and down 1.96 steps, 1.96 standard deviations, how much data do I catch? 95%. So how certain am I that I caught the real mean as I have my 8th puberty? 95% sure, because I caught 95% of the freaking data. There's only a 5% chance I'm wrong because I left out 5% of the freaking data. Do you guys see what I'm saying? So now I want you to realize, this is not what a problem is going to be like at all. These problems are really going to be very short and sweet. I'm trying to show the whole idea here. So to put all this stuff together, I want to start at the mean, and I'm going to go up and down, don't I? Give or take. I think it's this, give or take. Up and down, this many standard deviations. Isn't that basically exactly what we had up here? I just have a plus or minus in there, of course. Why? Because there's actually 2 data points I want, the upper one and the lower one. I want to go up and down from the mean. How are we doing? Incredibly enough, this is called a confidence interval because it's an interval based on a level of confidence. Again, math people not very creative in the naming department, but at least we get to the point.
Like 95%.
And so in this case, I'll be 95% confident in that interval, that interval is telling the truth, that the mean is caught in there. So what's the mean that we found? 41,980. How far up and down do I have to go? 1.96. The plus or minus is built in. You guys see that? Don't put a negative in there. That doesn't make any sense. The plus or minus is built in. 1.96 new standard deviations, because now I'm talking about samples of size 80, right? So what was that? 8,122. was the old standard deviation divided by the square root of 80 to get the new standard deviation. This piece, incredibly enough, this piece is called the error. Why do you think it's called the error? Because it's how much you think you are off by, right? We got this from our sample, but ain't no way somebody's going to say, well, that's exactly the answer. We're going to say we're off by, I think, this much, give or take this much. So what I would suggest to you is figure out the error first. Some of the homework actually only asks you for the error. So figure out the error first. 1.96 times 8,122. I can do this. Let me catch up to you. Okay. 8122. No. Okay. 1.96. Square root. Oh, I hate this stupid calculator. 22 divided by 80 square root equals, there you go, times 1.96. What do you get? 17?
1779.8.
I love it. 1779.8 is fine. 41,980. So we'd say we think that the real average income in San Diego is 41,980, give or take 1779.80. Cool? So I'd actually round it to like, yeah, just to be money. And then you could figure out what you could just subtract that from this, add this to this, to see what you think it's between. Shoot. You just lost. Yeah, that's too bad for you. So it'll be 40200.2. Oops. 0.19. To whatever you get when you add that. That'll be 4, 3. This is really 7 maybe. Ah, screw. 401.
402.0.1.
Yeah, 4, 3, 5, oops, 7, 5, 9, 8, whatever. So I can tell somebody that I'm 95% confident that the real mean is in between there. Right? So let's do a problem real quick. This will be the last thing. Let's do a problem real quick from start to finish without me embellishing in the middle, explaining why it works. Just to show you how quick these are. These set themselves up. The hardest step in these will sometimes be figuring out what the z-score is. And I'll show you an example of what I mean. So say we take a sample of 32, and we find an average shoe size of 10.98. And we know the standard deviation of shoe sizes is 1.913. Sure. These are men's shoe sizes, by the way. Yeah. First question I have is, why am I allowed to use a z-score both in this problem and this problem? What is it about the problem that tells me I'm allowed to use a z-score in relation to these percentages? There's no P and Q here. Talking about sample means, not percentages. It's not an NPQ problem, right? What's the sample size in both? Here was 80, which is bigger than 30. Here's 32, which is bigger than 30. So they're both normal enough, right? So if I said n equal 27, it better somewhere say it was normally distributed to begin with, because that's not enough, right? So watch out for that. Little hint for your future quizzes and tests from me. So the formula is just this. So the only thing I'm missing is how confident we want to be. Let's say I want to be 92% confident. How do you find the z-score for that situation? And how is the confidence interval always drawn? Am I not starting from the middle and going up and down? So how many tails will it always make? 2 tails, right? That will become very important later. in this class. But right now, can you guys see why I say it's got two tails out there, right? How much is in the middle here? 92%. So how much is on the side? 4%. So if you look up 0.04, you'll get the negative z-score, and the positive one, same number, just this positive, right? So what's the closest you can get to 0.04 area? Closest I can get is 0.0401, and that's a 1.75, right? So I have to go down 1.75 and up 1.75. So these confidence interval problems are actually pretty damn easy. They basically give me everything except the z-score. I've got everything else I need here, don't I? What's the mean? 10.98. Give or take 1.75. New standard deviations. The old one was 1.913. Square root of 32. Right? So mathematically, these are very simple to set up. The idea is pretty simple. I sometimes call it throwing a net out. If I want to catch only 92%, I can throw a smaller net out than I had to for 95%. That's why I only had to go out 1.75, not 1.96. I don't have to catch as many fish. I want to be a little less sure on this one, right? It's just going to come out smaller than it would have been otherwise. So the error here, let me see. I hate this calculator. Okay. Oh crap. All right. 32 square root. Yeah, I get 0.592. What you got? Yeah. Like 0.592 is fine. Yeah. Right? Then you add it to the 10.98. You subtract it from the 10.98, right? That's the idea. Right now I can say I think it's this. This is the, I can't remember what these, shoe sizes. Average shoe size 10.98, give or take a little more than half a shoe size, right? Or I could say it's anywhere from what would it be, Jeff? 388? Is that right?
Yeah.
To 11.572? So you'll love this. Here's the last thing. We are 92% confident that the interval 10.388 to 11.572 contains the true mean shoe size. You will have to write a sentence like that. An interpretive sentence. It's one thing to get the numbers. It's another thing to know what the hell those numbers are you just got. So obviously we'll do more of these next time. I'll have a handout next time. We should finish up chapter 7 next time, actually. Once you get this kind of down, the rest of them go pretty quick. Cool. And we have gone over, so makes up for all the other early times we got out. Yeah?
Would that be 10.788?
That's a 3. He's trying to be a 3.
Oh.
Yeah. It's just these numbers here.